Good day everyone! Today, we're gonna have a short review or a short recap to all the lessons that we have covered this second quarter in chemistry. Since our periodic exams are coming up, we are all in a hurry to review, of course. We want to get that high score that we all have been aiming for. But during our review, we all encountered some terminologies, some words, some topics that we have difficulties understanding because they seem difficult for us to understand. So don't worry, I have you covered. So today, we're gonna be covering each topic one by one, explaining them in simpler terms, simpler terminologies, giving examples that I hope you, I, and we can all agree on and understand. So let's start with week 1, the 3 states of matter: solid, liquid, and gas.
A liquid has a definite volume but no definite shape, taking only the shape of its container. Its molecules are close together but they can move and slide past each other, allowing the liquid to flow. The forces of attraction between the molecules are moderate, making liquids less rigid than solids but denser than gases. A solid is a state of matter that has a definite shape and volume. Its molecules are tightly packed together in a fixed pattern, allowing very little movement except for slight vibrations. This close arrangement gives solids their rigidity, density, and resistance to being compressed. A gas is a state of matter that has no definite shape or volume. Its molecules are far apart and move rapidly in all directions, which allows gases to expand and fill any container they occupy. The forces of attraction between gas molecules are very weak, making gases easy to compress and allowing them to spread out freely.
Now that we have finished discussing about the 3 states of matter, solid, liquid, and gas, let's now discuss about the atomic theory. Now, in the atomic theory, there are a bunch of scientists and philosophers who actually helped our people or scientists progress of how we perceive atoms as of today. So, the first scientist that we have in our timeline in atomic theory is actually Democritus. So, Democritus is a scientist who called atoms atomos. So, he was one of the first scientists who discovered or took interest in atoms. So, Democritus believed that all matters is composed of small indivisible particles called atoms. So, his discovery was more like a philosophy because he wasn't actually able to prove it, or he wasn't actually able to provide a model for the atomos that he called. Next is John Dalton with the solid sphere model. John Dalton believed that all atoms are invisible and compounds are combinations of different types of atoms. So unlike the other models, he actually believed that compounds are combinations of different types of atoms. The next model that we have is J.J. Thomson's plum pudding model. So what's unique about the plum pudding model? Because it's one of the first models that actually showed that there are different types of particles in an atom, which is the electrons and the protons. So that's an interesting fact that he believed that there is a pool of positive energy and the negative charges are embedded within it. The next scientist that we have is Ernest Rutherford, who created or discovered the nuclear model. So he was one of the scientists that had a nucleus in his model. So what is the nucleus made out of? A neutron and a proton. So neutrons having neutral. So its charge is actually neutral. Zero. It cannot be zero. It cannot be negative. It cannot be positive because it's like the balance of the positive and the negative charge. So he believed that the electrons' paths are actually predictable, and he actually discovered that most of an atom is actually space, and he discovered that most of the weight of an atom actually consists of its Actually, most of the weight of the atom he discovered from his gold foil experiment comes from the nucleus. The next model is Niels Bohr's planetary model. Now, unlike Ernest Rutherford's nuclear model, which he can only predict the movements of the electrons, Niels Bohr's model, planetary model, actually tells us that it is actually the paths of the electrons are actually fixed. So it is not randomized. Okay? So it's like the upgraded version of Ernest Rutherford's nuclear model. But there's actually a next scientist that contradicts both the nuclear model and the planetary model, which is Erwin Schrödinger's quantum mechanical model. Because in the quantum mechanical model, of course, just like the two models, the nucleus is in the middle, but he actually believed that the electrons are actually placed randomly around the nucleus. He believed that it was not within a path, it was not within an orbit, but it's like a cloud. Okay, the movements are unpredictable. We don't know it. We don't know how much we don't know the path of the movement of their electrons. So unlike these two, okay, he actually contradicts both of them, which summarizes the theory and the evolution of the atomic theory. Now let's summarize. Democritus, atomos, invisible, and makes up matters of the small particles that he called atoms. John Dalton, solid sphere, all matters made out of different sizes of atoms, and all compounds are combinations of different types of atoms. Atoms cannot be destroyed nor created. Next is J.J. Thomson, embodying full of positive energy embedded with negative charges, which we call electrons later on. Next is Ernest Rutherford's nuclear model. We discovered that atoms are mostly made of space, and we can predict the path of electrons. Niels Bohr planetary model. There is a fixed path of electrons, and Erwin Schrödinger contradicts both of them, and the path of electrons are completely randomized. So that's the summarization of our atomic theory. So let's move on for the next topic. Let's now tackle about pure substances. Now before we tackle pure substances, let's first know what are pure substances and how can we tell if something is a pure substance. A pure substance cannot be broken down by normal means, such as filtration, distillation, evaporation, or any other physical separation method. They also have fixed compositions, which means their chemical makeup remains uniform throughout the substance. Now, pure substances can be broken down to three: elements, molecules, and compounds. Now, how can we tell if something is an element? Now, we can tell if something is an element if there is only one type of atom. Let's say in gold, only one type of atom is present, which is gold. Next is oxygen. Oxygen only has one type of atom, which is oxygen. Now let's move on to molecule. How can we tell if something is a molecule? Now we can tell if something is a molecule if there are two of the same type of atoms present. Let's say in O2, oxygen gas. So we can see we have oxygen right here, and we have two, which tells us that there is two types of the same atoms or two oxygen in oxygen gas. Next is nitrogen or nitrogen gas, and two, there is two nitrogen in nitrogen gas. Next is compound. How can we tell if something is a compound? We can tell if something is a compound if there is two or more different types of atoms. Now let's break down H2O. In H2O, okay, we have hydrogen and we have oxygen. Hydrogen and oxygen are two different types of atoms, and that's what makes up a compound. But can a compound be a molecule? The answer is yes, of course. A compound can be a molecule, but a molecule cannot be a compound because they have different principles. Now, we can tell that a compound can be a molecule because, as an example, in H2O, there is two hydrogen in H2O, which tells us that compound can be a molecule, but molecule cannot be a compound because there would be another or a different type of atom. And if there is a different type of two or more different type of atoms present in a combination, it's gonna become a compound, and it cannot be a molecule nor an element. Now let's summarize. An element, there is only one type of atom. In molecules, there is two or more of the same type of atoms present. In a compound, there is two or more different type of atom that is present. So that is all for the pure substances. Now let's tackle about the average atomic mass computation. Now, before we tackle about the average atomic mass computation, there are three concepts that we must understand. First, isotopes. Second, the percent or the percentage of the abundance. The third one is the atomic mass. Now, what are isotopes? Isotopes are same atoms or same elements, but they differ in neutrons. They have the same protons, same electrons, different neutrons, which means giving them a different mass. Now, this is the formula that we must use. Sigma notation, M1 times F1 plus M2 times F2. That is the standard formula. But, depending on how many isotopes does your element have, you may extend it to M3 times F3, M4 plus times M4, and so on, depending on, again, how many isotopes. Now, since silicon has 3 isotopes, I am using till M3 times F3. What does M1 and F1 represent? M1 represents atomic mass, F1 represents the percentage abundance. First step that we must do before we use the formula is you must first convert the abundance to its decimal form and then multiply. Now, let's do some substitution. 92.230, when we convert it to its decimal point form, we get 0.92230, and then we multiply it to its mass, 27.977, we get 25.80. Same for the other isotopes. For 28.976, we get 1.35. For 29.974, we get 0.93. After we get all of those products, now we must add all of them to get 28.08 for silicon, and we always use the unit AMU, which represents the atomic mass unit. Now that's all for the atomic mass average computation. Now let's tackle about covalent and ionic bonding. But before we cover covalent and ionic bonding, there's one concept that we must understand first, which is the valence electrons. Now, what are valence electrons? Valence electrons are the electrons that a certain element can give or share to another element. But where can we find these? Or how can we know how many valence electrons does an element have? A valence electron can be found in the outermost shell or the outermost orbit of an element. Now, we can tell the valence electron in the periodic table according to our illustration. Now that we know about valence electron and how many valence electrons does each element have, let's now cover about the ionic and covalent bonding. In the ionic bonding, an element loses its valence electrons, which means it gives its valence electron to the other element. This type of bonding happens between a metal and a non-metal. The best example that we can give is between Na and Cl, which creates salt. Na only having 1 valence electron and Cl having 7 valence electrons. Now, for an element to be stable, it needs 8 valence electrons in total. But Cl only has 7. Now, Na will give its 1 valence electron to Cl, making it an 8 valence electron element, making it stable. So it loses its one valence electron, gives it to Cl, and Cl gains 1 valence electron. In the covalent bonding, an element actually shares its valence electron with another element. This happens between a non-metal and a nonmetal or a metalloid. Another example that we can give is H2O. There is two hydrogens and one oxygen. Now, oxygen having 8 valence electrons, which means it needs 2 valence electrons to be stable. Hydrogen having 1 valence electrons, it shares its valence electron with oxygen, giving it 2 valence electrons in total, giving it 8 or making it 8 valence electron, making it total. So, in the summarization, ionic bonding, you lose your valence electron and give it to the nonmetal, while the covalent bonding, we actually share and we do not lose. So that's our coverage for the ionic and covalent bonding. Now we're gonna tackle about the development of the periodic table. Now in the development of the periodic table, we had many key scientists that tried to or actually help improve the periodic table. But since there are many key scientists, physicists, philosophers that help improve the periodic table, we're only gonna cover some. So first, John de Bruijner, 1829. John de Bruijner actually proposed us the law of triads. So in the law of triads, he grouped the elements into sets of 3. So in those sets of 3, the elements had the similar chemical properties and atomic masses. Next is John Newlands, 1863. He proposed the law of octaves. So what is the law of octaves? In the law of octaves, in each 8 element, they have similar properties. Next is 1864, Lothar Meyer. Now, Lothar Meyer was actually one of the first scientists to release a periodic table that is according to or the arrangement of atomic masses. But that's not the main help of Lothar Meyer. Lothar Meyer actually helped group 28 elements into 6 families. So those 6 families had similar properties in physical and chemical. The next scientist that we have on our timeline is actually Dmitri Mendeleev. Dmitri Mendeleev was actually known as the father of the periodic table. Just like Lothar Meyer, his periodic table was arranged in the matter of increasing atomic masses. But why wasn't Lothar Meyer also known as the father of the periodic table when they both arranged it in increasing order? Well, Dmitri Mendeleev actually left a new path or a new door for other scientists in the future because he actually left gaps in his periodic table for the elements that he believed was actually discovered and wasn't actually introduced in the public yet or was to be discovered in the future. The next scientist that we have is William Ramsay. William Ramsay was actually the scientist who introduced us and discovered the 18th group in the periodic table, which is now known as the noble gases family. The next scientist is Henry Moseley. So Henry Moseley was actually the scientist who used X-ray to determine the atomic number of the elements, and now he was actually the pioneer or was the person who helped the modern periodic table, which uses the order of increasing atomic number, not atomic masses. The last scientist that we have in our timeline is Glenn Seaborg. So Glenn Seaborg discovered the lantanides and the actinides. So he actually discovered like a whole new other group or family of elements. But he also helped modify the periodic table. How? Because he placed the lantanides and actinides below the main table, which actually the format that we use today. So that's all for the development of the periodic table. Now let's tackle about the Bohr model and the Lewis dot model. For the Bohr model, we have 2 rules that we must remember. First rule, per shell they can only have a specific number of electrons that they can have. The Bohr model, in the first shell, we can only fit 2 electrons. The second shell, we can only fit 8 electrons. The third shell, we can only fit 18 electrons. And for the fourth shell, we can only fit 32 electrons. The second rule is that we can only put electrons in the clockwise method, not in the counterclockwise. Now, if I'm going to the right, you cannot go to the left. Now, each dot or each circle that we have here represents 1 electron. Since Cl or chlorine have the atomic number of 17, we need to put 17 dots or 17 circles in our orbit. Now, for the first circle, we have 2. For the second circle, we have 8. For the third circle, we have 7. Now, from what I discussed from the ionic and covalent bonding, the final shell or the outermost shell which contains the valence electrons. So in here in the third shell, we have 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Now, for the Lewis dot method, it's like the simplified version of the Bohr model. We've actually already used the Lewis dot method when we were discussing about the ionic and the covalent bonding. Each dot is equal to 1 valence electron. So unlike the Bohr model, which we actually put in all the electrons since this has 17 atomic number, we put in 17 dots or 17 electrons. In the Lewis dot method or the Lewis dot structure, we only put the valence electron. Like here, in neon, we only put 8 instead of 10. So the 8 valence electron is already there. In chlorine, in carbon, we only put in a 6 instead of its atomic number. So this is the simplified version or the simplified explanation of the Bohr and Lewis dot structure. For the final topic that we will review for this second quarter in chemistry, it's gonna be the electric configuration and the Aufbau principle. Now first of all, let's explore or know what's the Aufbau principle. So according to the Aufbau principle, the electrons first fill the lower levels before going to the higher levels. Now, let's move on to the electric configurations. The electric configurations actually have subshells, which is the S subshell, P subshell, D subshell, and the F subshell. Each subshells can hold a specific amount of electrons. The S subshell can hold 2 electrons. The P subshell can hold 6 electrons. The D subshell can hold 10 electrons, and the F subshell can hold 14 electrons. Now let's see how can we use these. Now, we will follow the diagonal method as same as what we're gonna show in the illustration. Now that we know from our illustration that we're going to start from the bottom being 1s, going all the way to the top being 7f. Now, let's see how we can actually use that. So our example that we're gonna be using is Cl, chlorine, Cu, which is copper. Now, for Cl, we have 1s with a value of 2, 2s with a value of 2, 2p with a value of 6, 3s with a value of 2, and 3p with a value of 5. Now, keep in mind that chlorine has the atomic number of 17. Let's count the electrons to see if we're correct. 6 plus 5 is 11. 11, 12, 13, 14, 15, 16, 17. Now that we know that we're correct, can we actually use the electric configuration method to know the number of valence electrons does an element have? The answer is yes. We can absolutely use the electric configuration method to figure out what's the total amount of valence electrons does an element have. Now, let's get started. The first step that we must do is find what has the highest energy level. How do we do that? These numbers from the start are called energy levels. 1, 2, 2, 3, 3 are called energy levels. So, there's actually 2 high energy levels that we have in Cl or chlorine, giving us 3s and 3p. So how do we get the valence electron? We will add the value or the electron value of 3s and 3p. 3s has the electron value of 2, 3p has the electron value of 5. When we add them, we get 7, giving us the total electron value of 7 valence electron. Let's move on to copper. Copper doesn't actually, in most periodic tables, copper's valence electron is not actually clearly stated. So, using the electric configuration method, we will now find that out. So, in copper, what has the highest value? Can you see it? 4 has the highest energy level. So, since there's only 1, we do not need to add. So, we only have 1 valence electron. So, that is all for the electric configuration method. Thank you very much for listening.